All right, thank you for coming this morning. So today I'm going to talk about a topic that's near and dear to my heart, which is about decision theory. And so I'm going to be talking about how to get from machine learning outputs, which are produced by neural networks or other kinds of models, and they're kind of free-form numbers, and you go to a lot of trouble to crunch a bunch of data and get these outputs. And then the question is, well, okay, now we're awash in numbers. What can we do with these? So the problem that we find ourselves in is that sometimes we get a little bit distracted about the difficult, interesting part of the problem, which is to produce predictions or forecasts or other kinds of outputs. And then we lose sight of what the bigger picture might be. And so I'm going to talk about how we can fit that machine learning model into a bigger context in which we're more focused on solving a problem. So examples of the kinds of problems that I'll be talking about in a very general way today. First of all, my first example is some kind of a recommendation. If we knew a list of purchases that a person had made before, what kind of advertisements could we show to those people? So we have a choice between showing an advertisement of one kind or another kind, or perhaps no advertisement at all. And we have to select among these on the basis of what we have recorded. Another kind of decision problem is if you knew someone's personal data and their history of a subscription to a service, then if they wanted to quit the service, how could you induce them to stay with the service? So you might give them some kind of a freebie, or you might give them a reduced rate, or some other kind of inducement to persuade them. And so you have a choice between different things that you could offer them. Another example is if you knew some demographic data about a person and had some medical test data, is it necessary to order another medical test? So clearly there are trade-offs here. If you order a test that's unnecessary, then that can be expensive. But on the other hand, if you miss some kind of a medical condition, then that can be expensive as well. So you have to weigh these things. And finally, here's yet another example. If you knew the history of earthquakes in the region and you know something about geology, then what should you do in order to prepare for an earthquake? So you might do things like strengthening your house foundation, or stocking up on food, or organizing neighborhood help groups. So these are all possible actions that require different kinds of investments and that might have different kinds of benefits in the case of an earthquake. And of course, there's also the possibility that there won't be an earthquake. So then the question is, how much are you willing to invest if nothing happens? So in all of these examples, the common elements that we see are that we have the opportunity to select from different actions. So so different alternatives present themselves to us, and we have to take one of them. The other elements of this that I'll be emphasizing in this talk are that we have beliefs about what might happen, and we also have preferences. Preferences being a measure of how much we prefer or value or like or appreciate different outcomes. And so the problem that we are faced with is that we don't know exactly what's going to happen, and so we have to choose an alternative based on the uncertain beliefs that we have and taking into account our preferences. So this is the problem decomposition that I'm going to emphasize in this talk, which is to separate the beliefs and preferences. And this is in this decomposition, the beliefs are often the part that is the most difficult to come by. So we have a collection of facts, and we will infer from these our beliefs. And then preferences are a little more fuzzy in the sense that these are tied to assessments or values that different individuals might have. So so we're kind of, by separating beliefs and preferences, we're kind of separating these two aspects: the value part of it that's more personal, and the belief part that is more tied to facts. So I'm going to be using different terms interchangeably with respect to preferences. We might call these values, or we might call these payoffs in different contexts, or we might call them costs and benefits. So it's in machine learning, it's not necessary to separate beliefs and preferences. There are machine learning models which combine these into a single function. And an example of that is in reinforcement learning, which was illustrated by the Flappy Bird example yesterday. So I won't say more about that, but I just want to emphasize that the separation of beliefs and preferences is not a fundamental feature. It's also something that can be combined in machine learning. So so when we are working in a machine learning context, typically the beliefs are going to be calculated by our machine learning model. So, for instance, in the examples that I was presenting before, the machine learning model might be calculating something about the reaction of a user to an advertisement. And the preferences can often be handled by what amounts to a simpler post-processing step on the machine learning outputs. So it's not always the case, but in many cases, it's after having gone through a very complicated machine learning model, multiple layers, neural networks, different kinds of models. In comparison, taking the preferences into account is computationally much simpler. And I'll go through an example of that, which is very simple, but also illustrates the essential features of the calculation. So the reason that I'm emphasizing preferences here is that these often express important business logic. So the values that we attach to different outcomes, when we do that, we're expressing what we know about how the problem works, how the whole system works. So we can attach assessments to the values of medical outcomes or earthquake events or reactions to advertisements. And in every case, these represent something about what we know how the whole problem works. The other aspect of business requirements that enters here is that the constraints on the possible actions are also an expression of what we think is possible. So we're also building in something about what we know about the problem in that step. So when we say that the possible actions include A, B, C, and D, but not E and F, that's stating something about what we know about how the problem works. Whoop. So I mentioned that we'll be talking about decision theory. So just very quickly, what do we mean by a decision theory? So it just means a formalization of a way to derive the action that's preferable or chosen from other considerations. And we will be deriving actions from beliefs and preferences. Whoop, good heavens. So we are going to look at a normative theory, which means that this is a rational way to go about making decisions. This isn't intended as a description of how humans actually make decisions, because we are not completely rational. So humans approximately carry out this process, but not exactly. And so that's a very fascinating topic in itself, but we're going to stick to what is rational in the sense of, if we were going to do this with a machine, how would we program it to do this automatically? So the particular form of decision theory that I'll be talking about today is the so-called expected utility decision theory. So in this theory, the rational choice is to select the action that has the greatest expected utility. Utility, in this sense, being the formalization of preferences. So what we mean by expected in this context is that the utility or the value is averaged over our beliefs about different outcomes. So it's an expectation in the sense of an average. So a standard paraphrase of this theory is that the value of a lottery ticket is what its expected payoff is. And that if we have a choice between purchasing different lottery tickets, we should purchase the ticket that has the greatest expected payoff. So the mapping between this simplified form and a more general form is that our choices correspond to buying different lottery tickets, and the payoffs correspond to the costs and benefits associated with those. So the formal statement of this is that the expected utility is just the weighted sum of the utilities for each action in each state of the world. So states meaning the possible outcomes that could be happening, such as the person has a medical condition, does not have the medical condition, or that a picture includes a person or a dog or a car or something else, or that a text contains a friendly message. So these different possibilities are the possible states of the world, and the expectation is taken over the probability that we are in one state or another. So it turns out that this summation is really at the heart of the whole decision procedure. So this is I'll talk a little bit more about generalizations of this, but it doesn't get too much more complicated than this. So if we're going to put this theory into action, we need to look at the different parts of it. The first problem is to identify the set of states over which we need to compute beliefs, and typically these are going to be outputs of our machine learning model. We also need to identify the set of possible actions. So for any particular situation, we can have as many alternative actions as we wish. And these, again, are going to be, what we consider to be the possibilities are going to be a representation of what we think about how the problem works. So we can bring business requirements into the picture this way. And for each pair of the possible action and the possible outcome, we need to assess the utility. That is to say, we need to assign a value to it. Just a side note, it's possible to express this whole theory by looking at expected cost instead of expected benefits, and that just means that you change all the positives to negatives and vice versa. And it works both ways. I find it easier to keep it straight if I think about benefits being positive. So I'll just mention some of the machine learning models that output probabilities, and these include some of the most commonly used ones. Logistic regression, often used in classification, neural networks with logistic output, which is a generalization of the logistic regression, the neural networks with softmax outputs, yet another generalization, the naive Bayes model that's often used in classification. Those models that I mentioned are all directly giving probabilistic outputs, and many other models can be formulated that include can also give probabilistic outputs. And there are important classes of models from which probabilities can easily be derived. I'll just note here any kind of a regression model that has additive noise. That is to say that you think that your output is going to be, you're kind of shooting for the middle of the cloud, and your output function is going to be the smooth part of the function, and the cloud is going to be represented by some variance around that. So models of that kind can easily be arranged to give probabilities. So examples of these are linear regression and neural network regression models. So I'll very quickly mention that not all machine learning models give probabilities, and therefore not all machine learning models can be fit into this expected utility framework. So an important case is the support vector machine, often used for classification. And I'll just mention that the support vector machine is essentially going straight from the inputs to the assignment of class labels and skipping the intermediate step of probability and expected utility. So if you're working in an expected utility framework, my advice is perhaps use a different classification, such as a neural network classifier. Another important example of a non-probabilistic model is the random forest, which is, as it's implemented in R, is a not quite probabilistic. It uses a voting scheme among a number of randomly generated tree models. And I think that it would probably be possible to easily modify this to give an exactly probabilistic output. So let me just mention, I'll walk through a very brief example. And so I apologize that the text might be a little hard to read, but we'll go through this in detail so that I hope that it will become clear. So the first part of our expected utility calculation is to assign probabilities over possible outcomes. So what I've assumed here that we have the two probabilities, which are the end result of some complex calculation, which may have been very time-consuming and very difficult to come by. But we're just looking at the tail end of it. Here we have the probabilities as a given. And here are the utilities for each of the possible action and state pairs. So this array U has a number of columns equal to the number of states in the probability list, and it has a number of rows equal to the number of possible actions that we're considering. So these values are something that I'm assuming are going to be assessed for each one of the action state pairs. So as I was saying, it's necessary to calculate this weighted sum for each of the actions, that is to say, each of the rows, and find the maximum element. And then that's going to be our recommendation of what the rational action is. So just to be explicit, all we need to do is to calculate these three terms here, which are multiplying the elements of P and U and adding them up. So just to walk through this very carefully, so the first step is to compute the expected utilities, and the second step is to find the index of the greatest element. So going through this again in detail, so starting with the probabilities and utilities, the essential calculations that we need to do are to multiply the probabilities times rows of the array U and add them up. So this is P times the first row and add it up. This is P times the second row and add it up. This is P times the third row and add it up. And again, in a more Pythonic fashion, we're going to tie together the elements that need to be multiplied together. That's the first row and the second row and the third row. And again, what we need to do is to go ahead and carry out that operation, first row, second row, third row. And now we'll go ahead and add up those pieces, first row, second row, third row. And now just to go back to where we were before, this is building on the previous steps. Here we do the whole thing at once, and we find these are our expected utilities. That is to say, the weighted sums of the utilities. And you see that the greatest value is 3 in this case, and its index is 2. That means that in this case, we recommend the action corresponding to row 2. So again, to put the whole thing together, this is the statement that I showed before. First, calculate the expected utility, and then find the element that has the greatest value. So just to, I know that this is a very simplistic computation, and it turns out that this is exactly the kind of computation that you need to carry out when you go through this expected utility decision. So this is a very simplistic problem with just 2 possible outcomes and 3 possible actions. So what about more general problems? What if there are more actions to consider? Well, that just means that we're going to have additional rows in U, the utility list. And what if there's more than 2 discrete states in the possible outcomes? That means that there's going to be additional columns in U, and there's going to be additional elements in the probability vector or tuple. And what if the states are continuous instead of discrete? That means that the expected utility calculation is going to be an integral instead of a summation, going from the discrete to the continuous case. And what if actions also are continuous instead of discrete? Then we're going to be maximizing over a continuous function. So in each case, where there's an obvious way to go to the more general case, building on the very simple weighted sum that we started out with. So just to summarize, in order to get from our machine learning outputs to a decision, we're going to separate the different aspects of the problem. We're going to consider separately the beliefs, which are a statement of of what we believe is happening in the sense of our rational assessment or rational degree of belief of the different outcomes that are possible. And we're taking that apart from our assessment of how much we value or prefer those different outcomes. So, and just to summarize the essential step of the decision procedure, we'll compute the expected utility for each possible action, and pick the action that flows to the top of the list. And in many cases, this expected utility calculation is much simpler than the other steps which brought us to that point. So as we are going now from here to putting this into practice, some ways of going forward here. I would like to recommend that you can bring business requirements into play via the utility function and also via constraints on the set of possible actions. So these are ways in which the outside world comes into play directly into the decision process. I believe that in many cases that the utilities and the set of possible actions are things that are very changeable in a real-world problem-solving context. What you consider the possibilities will change, and as you learn more about how the problem works, you may assess utilities differently. So one possibility is to make the utility and possible action list part of the configuration data for any implementation, so that it's something that you can go back and iterate on and change easily and bring new information into play. I believe that the formal statement of preferences is a great way to get input into the process from stakeholders, and at the same time, this is insulating the large mass of the machine learning code from changes. So instead of mixing these things together so that changing one thing implies changing something else, instead we have we may be able to have a machine learning pipeline that's largely unchanged while the preferences aspect of it is more changeable. However, a key point here is that it's on the basis of the expected utility calculation that we need to determine what the outputs of the machine learning pipeline need to be. So when we talk about assessing different actions in different contexts, those different contexts are going to be the outputs that we need from the machine learning pipeline. So we're essentially starting at the tail end and working backwards towards the machine learning pipeline. So summary of it might be that we'll start with the decision step and then work backwards from there to determine the structure of our machine learning pipeline. So that brings me to the close of my talk, and I'd like to thank you all again for coming.